Welcome to Between Sleep and Science. Earth stands alone. It is the only known world in our vast cosmic neighborhood that nurtures life. What makes our planet so uniquely special? The answers are etched deep within the planet's own turbulent history. To truly grasp this rarity, we must journey back in time. We're traveling to an era when there were no continents, no oceans, and no familiar blue sky. You will witness a world forged in fire, defined by epochs of icy darkness, and shaped by long, slow geological breaths. We will trace the path from the primordial seas to the first islands, quiet hints of future land masses emerging from the deep. We will feel the heat of ancient oceans, the chill of great glaciations, and discover how this ever-changing nature built the home we inhabit today. If these quiet wanderings bring you even a moment of calm, feel free to leave a few warm words, or tell us in the comments which city you're watching from, so we can see how far our explorations travel. You can also simply like and subscribe. Your support helps other weary hearts discover this cozy corner. And now, you don't need to do anything at all. Just settle in comfortably and let the slow, steady rhythm of deep time gently carry you away from your worries. Let the journey begin. The chaotic dawn. 5 billion years ago. The Hadean Eon. Our story begins almost 5 billion years ago. At this moment, Earth does not exist. Instead, a massive cloud of dust and fine particles, the residue of the sun's formation, orbits our youthful star. Within this cloud, there are no continents, no oceans, only the light of the newborn sun and a dense mixture of raw material slowly settling into the plane of the star's orbit. This initial stage, the solar system's birth, was a slow-motion dance of gravity and collision, where solid components emerged from the turbulent protoplanetary disk. The temperature gradient within this disk determined the composition of the emerging solids, refractory silicates and metals close to the sun, and volatile ices further out. If we accelerate time, we observe tiny specks of dust colliding under the pull of gravity, sticking together through electrostatic forces and forming miniature rocks. This accretion process is incredibly slow, almost imperceptible, but it is the starting point for the future Earth. It seems astonishing that something as complex as a planet could emerge from such simple, insignificant components. Yet, nature adheres to its fundamental laws. Over millions of years, these rocks continued to merge, drawing closer until they formed larger bodies, known as planetesimals. Gradually, among hundreds of protoplanets swirling around the young sun, one entity began to stand out: our future Earth. This phase of growth was characterized by violent impacts, each collision releasing immense energy that kept the accumulating mass in a molten state, forming a colossal magma ocean kilometers deep. This ocean was not a uniform liquid. It was fiercely stratified by density, with heavy silicates sinking and lighter ones floating, establishing the initial chemical layers of the planet before the final catastrophic event. The process of core formation began here, with heavy iron sinking toward the center, generating the first vestige of the planet's magnetic field. The fiery crucible and the cosmic impact. Around 4.54 billion years ago, the Earth had undergone gravitational differentiation. Its internal structure had settled into distinct layers based on density. The heaviest elements, primarily iron and nickel, sank inexorably toward the center to form the metallic core, a process that released vast amounts of gravitational energy, maintaining the planet's fiery heat and creating a massive churning heat engine that continues to power our tectonic plates today. Lighter silicates floated up to become the mantle and the earliest unstable crust. The planet was a hot, violently unstable world. Near the surface, temperatures exceeded 1,200 degrees Celsius, a normal, albeit terrifying stage in planetary birth. A solid crust was virtually non-existent, surrounded instead by a vast, shapeless flowing sea of molten lava, covering the entire globe like a burning shroud. The atmosphere was equally hostile, having been stripped away multiple times by solar wind and impact energy, only to be reformed by continuous, extreme volcanic outgassing. There was no air in the modern sense, only a thick, suffocating blend of carbon dioxide, nitrogen, and vast quantities of superheated water vapor constantly escaping from the magma ocean below. This primal atmosphere exerted pressures far greater than today's, trapping the heat and creating a runaway greenhouse effect. It was a world entirely unsuitable for life. Had you approached the surface, you would have been instantly consumed by an unbearable heat and the absence of oxygen. As this scorched, liquid sphere continued to take shape, one of the most consequential events in its history occurred. A large object named Theia, a protoplanet roughly the size of Mars, approached Earth, moving at approximately 15 kilometers per second, about 20 times the speed of a bullet. Theia's immense gravity distorted Earth's surface even before the physical impact, raising massive, fluid waves in the fiery ocean of lava. The resulting collision was perhaps the single most powerful event in the history of the solar system's inner planets. The surfaces of both worlds partially melted and vaporized, and trillions of tons of material, vaporized rock, dust, and debris, were instantly ejected into space, forming a massive synestia, a donut-shaped structure of vaporized rock. This colossal plume of superheated material reached far into Earth's orbit, briefly forming a ring of incandescent vapor. The impact was so energetic that it recalibrated the entire planet, increasing its rotation rate and establishing its current axial tilt. While the young Earth lost some mass, it gained something essential. The ejected material remained on a stable orbit and gradually coalesced into a dense ring. Gravity worked its magic again. Within just a few hundred or thousand years, that ring compacted into a large sphere more than 3,000 kilometers in diameter. The Moon's exceptionally large size relative to Earth is a direct result of this massive glancing blow, suggesting it formed predominantly from the mantle material of both Earth and Theia. This is how the Moon formed: a satellite that would play an immense role in the planet's subsequent development by stabilizing its axial tilt, moderating its climate, and driving ocean tides. Back then, the Moon was dramatically closer, orbiting at approximately 22,000 kilometers instead of the current 400,000 kilometers. Its size in the sky would have been dozens of times larger than it is today, a terrifyingly beautiful dominating spectacle over the cooling surface. The gravitational forces exchanged between the Earth and the close Moon would have caused immense tidal flexing and internal heating, accelerating the differentiation of both bodies and initiating the process of the Moon's slow recession from Earth. A rapidly spinning world and the coming of water, late Hadean. In the immediate aftermath of the impact, Earth rotated far more quickly due to the energy of the collision. A single full rotation took only 6 hours. The ultra-fast days generated relentless, hurricane-force winds and powerful tides. The close, young moon raised colossal gravitational waves that rolled across the entire superheated planetary surface, continuously churning the thin, fragile crust that was attempting to solidify. The friction generated by these enormous tides acted as a cosmic brake, slowly but surely lengthening the day, transferring angular momentum from Earth's rotation to the Moon's orbital distance. This effect is still measurable today, though vastly slowed, but time brought change, driven by the ceaseless escape of heat from the core. Earth began its long process of cooling. The extreme volcanic outgassing of water vapor began to encounter temperatures low enough to allow condensation. This began a period of torrential, planet-wide rain that may have lasted thousands of years. The first solid patches, made of dense igneous rock, basalt, and early granite, started to appear from the molten rock ocean, forming rafts that floated on the liquid magma. The gaseous atmosphere thickened further, and water vapor began to condense into dense clouds, blocking the sunlight. Although the surface temperature remained high, around 70 to 80 degrees Celsius, hot enough to scald, but below boiling point due to the high atmospheric pressure, it was steadily dropping. The early crust was subject to intense fracturing and resurfacing, a process often referred to as stagnant lid tectonics before the emergence of mobile plates. The most critical process was the accumulation of liquid water. Meteorites and comets, icy relics from the solar system's formation, continuously bombarded Earth, delivering vast quantities of water trapped within their structures. Because this rain of impacts persisted for millions of years, these extraterrestrial sources, combined with water vapor released from the mantle, contributed significantly to the formation of Earth's first water bodies. Liquid water gradually began to cover the surface, pooling in low-lying areas and forming the earliest hot, acidic, and mineral-saturated oceans. The early oceans would have been dark green, thick with dissolved iron and various metal ions leached from the newly formed crust. The high acidity from dissolved volcanic gases like hydrochloric and sulfuric acid prevented the rapid formation of large mineral deposits, keeping the early ocean in a dynamic, chemically aggressive state. The planet was taking the essential steps toward its future appearance. A global ocean, a dense, carbon-rich atmosphere, and a solidifying crust. Yet stability was elusive. Winds reached speeds comparable to the most destructive hurricanes known today. The moon continued its slow recession, pushing Earth's rotation to slow down. The chaotic young world was slowly transitioning toward a state of greater equilibrium, though the surface remained under constant bombardment, which occasionally sterilized the surface, vaporizing any water present, and making the foothold of life incredibly difficult to establish. The late heavy bombardment and the Archean dawn, 4 to 2.5 billion years ago. The period between 4 billion and 3.8 billion years ago is sometimes referred to as the late heavy bombardment. As the young Earth cooled, water carried by countless celestial objects finally stayed on the surface, accumulating in the first depressions. The temperature remained high, a true warm little pond globally, but this was enough for water vapor to condense and form a stable cloud cover. The solidifying crust grew denser and the surface more stable, forming small mobile proto-continents that were recycled rapidly through early forms of subduction. Around 3.9 billion years ago, Earth endured an especially intense final spasm of the late heavy bombardment. These celestial bodies brought not only impact energy, but also crucial ingredients, tiny inclusions of salt, water, and complex carbon compounds. Some meteorites, over 4 billion years old, still hold microscopic droplets of water and carbonaceous material, ancient traces of that distant time serving as potential building blocks for life. The gradual accumulation of water was the key. From isolated puddles, the first stable oceans began to form. Their composition was far from modern, hot, highly acidic due to volcanic gases, and saturated with dissolved minerals, including vast amounts of soluble iron. They were a dynamic, complex chemical cauldron, rich in sulfur and hydrogen, within which the conditions for future life were being born. Despite the relative weakness of the young sun, the faint young sun paradox, the sun was about 30% less luminous than today, the incredibly thick carbon dioxide and methane-rich atmosphere provided sufficient greenhouse warming to keep the planet from freezing entirely. The early life forms themselves may have contributed to this warmth by producing methane, a powerful greenhouse gas, from the hydrogen-rich environment. The first land and the architects of air, Archean Eon. Around 700 million years after Earth formed, something new emerged in this watery world, the first land. They arose where molten rock, buoyed by the underlying mantle, pushed through cracks in the crust. These upwellings formed volcanic structures that grew, cooled, and expanded above the ocean's surface. Though small and scattered, composed mostly of dark, dense basalt and primitive granitic rocks, these were the planet's first pieces of dry land, the precursors of future continents. The continuous process of plate formation and subduction, though likely faster and more violent than today, began to slowly accumulate the first cratons, the stable hearts of continents. These cratons, often made of lighter, buoyant felsic rock, resisted subduction and became the permanent foundation blocks of the modern continents. The continental growth rate was slow, with vast, shallow oceans covering most of the globe. The atmosphere, however, remained hostile, a reducing atmosphere. It was largely oxygen-free, dominated by carbon dioxide, water vapor, and nitrogen. Yet, the planet's chemical processes were gradually increasing in complexity. Around 3.8 billion years ago, deep within the lightless oceans, unique environments existed, hydrothermal vents. Seawater seeped deep into the crust, was superheated by magma chambers, saturated with gases and reduced minerals such as hydrogen, methane, and sulfur compounds, and then returned to the ocean under immense pressure. Many researchers believe that in these dark, hot, mineral-rich columns, isolated from the sun's harsh ultraviolet radiation and powered by chemical gradients, the very first organic structures, the self-replicating molecules like RNA, may have appeared. The sustained chemical energy and temperature gradients provided a stable environment, unlike the violent surface. While the precise moment life began is lost to billions of years of change, we know that by roughly 3.5 billion years ago, the oceans held the first single-celled organisms, simple, anaerobic bacteria that lived without and were intolerant of oxygen. These prokaryotes thrived in the anoxic soup, obtaining energy from chemical reactions in a world dominated by sulfur and iron. The earliest life represented a massive energy shift, moving from purely abiotic chemical reactions to biologically driven metabolic processes. They were the original energy converters, preparing the planet for a massive, irreversible change. The Great Oxygenation Event, Life's Poison. Over the next hundreds of millions of years, a profound change occurred in the shallow seas. Colonies of these microorganisms, simple in structure but revolutionary in function, began to form layered dome-like shapes, stromatolites. These were composed of countless bacterial layers bound with mineral particles. Inside these seemingly ordinary rock structures, a process was underway that would reshape Earth's atmosphere: photosynthesis. These ancient cyanobacteria harness sunlight, carbon dioxide, and water to produce energy, creating simple sugars. Crucially, the byproduct of this solar power was oxygen, O2. This massive release of oxygen did not immediately flood the atmosphere. Instead, it began the long, slow process of chemical purification. The early oceans contained vast quantities of dissolved, reduced iron. In the primordial ocean, the free oxygen immediately reacted with the immense quantities of dissolved iron, forming rust-red, insoluble precipitates. These iron oxides settled on the seafloor, creating the distinctive geological features known as banded iron formations. These formations, visible today as alternating red, oxidized iron, and gray, silica layers, are physical evidence of the episodic rise of oxygen in the ancient oceans. Layer by layer, the stromatolites silently produce oxygen, and layer by layer, the dissolved iron captured it. This process continued for hundreds of millions of years, acting as a massive global rust trap, creating sedimentary deposits that are today the source of much of our mined iron ore. The cessation of these formations marks the point when the oceans could no longer absorb all the free oxygen. Once the vast reserves of iron in the water were almost completely oxidized, a process known as the Great Oxidation Event, the excess oxygen finally began to bubble out of the water and into the air, creating a truly global catastrophe. This event, occurring around 2.4 billion years ago, was a vital step toward modern life, but it simultaneously triggered the first global environmental crisis. The sudden appearance of free oxygen was toxic to the dominant anaerobic life forms, a chemical pollutant that destroyed their energy pathways, leading to a massive mass extinction. This event, often called the oxygen catastrophe, represented a sharp evolutionary bottleneck, though some life forms survived by retreating into anoxic pockets or evolving antioxidant defenses, paving the way for the more complex, oxygen-breathing life that followed. The planet became a breathable environment for future life, but a poisonous gas chamber for the life of the time. Thanks to these silent architects, the first significant quantities of free oxygen appeared in the atmosphere, a vital component without which life in its modern form is impossible. Rodinia and the Slowing Day, Proterozoic Eon. The oxygenation event fundamentally changed the planet's chemistry and climate, paving the way for the Proterozoic Eon. The newly established atmospheric composition and the slower rotation of the Earth define this period. The reduced methane and CO2 in the atmosphere, stripped away by the rising oxygen, also triggered the first major, albeit localized, ice age, known as the Huronian glaciation, demonstrating the profound link between life and global climate. The release of vast amounts of oxygen oxidized atmospheric methane, a much more powerful greenhouse gas than CO2. This chemical cleansing catastrophically stripped the atmosphere of its warmth, leading to a massive and prolonged drop in global temperature. The result was the Huronian glaciation, which lasted hundreds of millions of years. This event, spanning from approximately 2.4 to 2.1 billion years ago, covered vast areas, demonstrating the planet's extreme sensitivity to biologically driven changes. During this long cold period, evolution slowed, but the surviving life forms, particularly the emerging eukaryotes, learned to cope with the presence of oxygen, laying the biochemical foundation for complex life. The Huronian ice sheet, which extended far into equatorial regions, serves as a sobering testament to the power of a tiny organism to completely overhaul a planetary climate system. In those distant ages, Earth's days were still much shorter. The planet's rotation was gradually slowing due to the tidal influence of the receding moon. From the initial 6-hour day, the rotation extended to approximately 16 hours after billions of years. This slowdown had major impacts on climate, winds, and ocean currents, reducing the extreme turbulence of the early world and allowing for more stable climate patterns. The energy transferred to the moon continued to widen its orbit, a phenomenon that has governed our planet's rhythm for eons. About 1.5 billion years ago, Earth began to acquire recognizable features. The surface consisted of many land masses, but their arrangement was constantly shifting. Deep beneath the crust lay the hot, mobile rock layer known as the mantle. The planet's internal heat drove slow but powerful currents in this layer, dividing the crust into large dynamic slabs, the tectonic plates. Over vast spans of time, these plates converged, collided, and separated, creating new oceans and land. The emergence of modern-style plate tectonics around this time led to the first stable continental masses. Around 1 billion years ago, these long tectonic processes culminated in the connection of various land masses, forming the supercontinent Rodinia, meaning motherland. This colossal landmass was concentrated largely in one hemisphere, near the equator, surrounded by a single vast ocean known as Merovia. Rodinia's climate was hot, the interior dry, and the surrounding oceans relatively warm. The sheer size of the supercontinent inhibited rainfall far inland, leading to massive deserts and high rates of erosion at its edges. The concentration of land at the equator also had a significant effect on ocean circulation, possibly contributing to the ensuing climate crisis by blocking warm currents from circulating to the poles. Life was becoming gradually more complex, though still microscopic, with the appearance of the first eukaryotes, cells with nuclei, and later, the first simple multicellular organisms. But the tectonic forces did not rest. Heat from the planet's interior, likely fueled by massive plumes of hot material rising from the core mantle boundary, began to stretch and weaken Rodinia's crust. Slowly, the supercontinent began to fracture. This rifting process was uneven and spanned millions of years, acting as a geological stress test on the continental lithosphere, pulling the land masses apart. Snowball Earth, the Great Freeze, the Cryogenian period. The breakup of Rodinia led directly to a series of climate catastrophes. As the continental fragments separated, they exposed massive amounts of fresh silicate rock to the atmosphere, particularly near the equator, where heat and humidity maximize chemical reaction rates. Silicate rock, when exposed, undergoes intense chemical weathering, a process where carbon dioxide, CO2, in the atmosphere reacts with the rock and water, drawing CO2 out of the air and binding it into solid carbonate minerals. This long-term drawdown of CO2 catastrophically reduced the planet's ability to retain heat, since CO2 is a powerful greenhouse gas, causing temperatures to plummet. Earth entered a period that would later be named Snowball Earth. Around 650 million years ago, the planet entered a global glaciation. Ice is highly reflective, high albedo. As ice sheets expanded rapidly from the poles toward the equator, they reflected more and more sunlight back into space, accelerating the cooling in a runaway positive feedback loop. Ice sheets eventually met almost at the tropics. The entire surface was enveloped in an icy shell several kilometers thick, an astonishing state sometimes called snowball Earth. Geological evidence, such as glacial deposits found in South Australia, supports the theory that ice extended to equatorial regions, with the entire ocean covered by a thick layer of sea ice. Surface temperatures may have averaged minus 50 degrees Celsius, creating a world of profound stillness and darkness. The snowball Earth state lasted millions of years, but the Earth's core remained hot. Volcanic activity did not cease. Eruptions occurred both above and below the ice. With the entire surface sealed by ice, volcanic gases were barely absorbed by the rocks, and chemical weathering ceased entirely. Carbon dioxide, continuously being pumped into the air by volcanoes, slowly accumulated in the atmosphere, creating a dense, insulating layer that began to trap heat. This slow but unstoppable buildup of carbon dioxide was the planet's internal mechanism for self-correction. After millions of years, the concentration of greenhouse gases became so high, hundreds of times the current level, that the atmosphere finally began to overcome the reflective power of the ice. The planet slowly warmed until the ice caps at the equator began to melt. This exposure of dark rock and ocean instantly dropped the albedo, triggering a rapid warming, another runaway effect, but this time in reverse. The ice sheets became unstable, leading to a monumental global thaw. The evidence of this rapid warming is seen in cap carbonates, thick layers of limestone deposited directly atop glacial till, formed by the sudden reaction of atmospheric CO2 with meltwater. As the ice retreated, more sunlight was absorbed by the land and water, accelerating the melting. This massive release of meltwater, combined with chemical reactions in the atmosphere, like ultraviolet light reacting with water to create oxygen-rich compounds, such as hydrogen peroxide, drastically increased the oxygen levels once again, purifying the oceans and atmosphere. By 600 million years ago, the climate had stabilized to resemble a mild summer day. Earth's day now lasted about 22 hours. The stage was set for life's most dramatic leap. The Cambrian explosion and the ozone shield, Paleozoic eon. The Great Thaw released a flood of nutrients into the oceans, which, combined with the higher oxygen levels, primed the world for rapid biological expansion. Prior to the global glaciation, life consisted almost exclusively of simple soft-bodied bacteria and simple ediacaran fauna. The few forms that survived the multi-million-year freeze, often near hydrothermal vents or in deep-sea refugia, became the foundation for massive evolutionary change. Around 540 million years ago, in the newly oxygen-rich oceans, a major surge in the complexity of life occurred, the Cambrian explosion. In a geological blink of an eye, the variety of life skyrocketed. Animals became larger, more complex, and, crucially, developed hard skeletons, armor, and segmented bodies for defense, locomotion, and anchoring muscle. The need for defense spurred the need for better offense, initiating a rapid evolutionary arms race that led to incredible morphological diversity. The first true predators appeared in the oceans, multi-eyed creatures with developed limbs, signaling the start of this intense competition. Trilobites, distant relatives of modern insects and crustaceans, spread throughout marine ecosystems, becoming one of the most successful groups of the era. Food chains became complex, with primary producers, herbivores, and multiple levels of carnivores, transforming the oceans into a place of rapid, dynamic evolution, filled with creatures whose fossils give us the first clear picture of animal life. Meanwhile, the land remained virtually barren. Solar radiation, specifically harsh ultraviolet UV light, was too intense for complex life to survive without protection. However, the rising oxygen levels were leading to the formation of a crucial atmospheric shield, the ozone layer. Oxygen molecules, O2 in the upper atmosphere were split by high-energy solar radiation and then reformed into ozone O3. This gas began to concentrate in the stratosphere, creating a natural screen against lethal ultraviolet radiation. This was the final piece of the atmospheric puzzle, making the land surface habitable by blocking the DNA-damaging UV wavelengths. The colonization of land and the age of forests. With this protection in place, the conditions on land began to change. Life faced new challenges on land: gravity, requiring structural support, desiccation, drying out, and temperature extremes. Around 375 million years ago, the first land plants appeared, simple, small organisms resembling mosses or lichens. They grew in wet areas, clung to the shoreline, developed waxy cuticles to prevent water loss, held the soil, and created surface layers capable of retaining water. This pioneering vegetation created the necessary microclimate for other life to follow by creating shade and humidity. Following them came taller plants, developing vascular systems, xylem and phloem, to transport water and eventually tree-like forms. At the same time, a fish in the ocean called Tiktaalik, also appearing around 375 million years ago, possessed features considered early limbs, a fishapod with wrist bones and robust ribs, suggesting it could prop itself up. Its fins were strong enough to support its body in shallow water. Over the next 15 million years, fish like Tiktaalik gave rise to the first true four-legged animals, the tetrapods. These early amphibians had to contend with the intense environmental pressures of the Devonian period, developing strong skeletons to counter gravity and specialized lungs for breathing air. By 360 million years ago, these creatures were confidently establishing themselves on land, opening the door for all future terrestrial vertebrates: amphibians, reptiles, dinosaurs, birds, mammals, and eventually humans. The development of vast, swampy forests marked the Carboniferous period. Plants grew ever taller, spreading further inland. Ferns, horsetails, and club mosses appeared, some reaching heights of up to 30 meters. These massive tree ferns formed the first widespread forests, dramatically increasing the amount of oxygen in the air through active photosynthesis. The sheer volume of plant life during this time was unprecedented. A new reproductive mechanism proved exceptionally successful: the seed. Unlike spores, which required water for development, the seed contained a moisture and nutrient reserve within a protective shell. This innovation allowed plants to spread into drier, less hospitable conditions, breaking the dependence on water for reproduction and leading to the rapid colonization of inland areas. This period, around 300 million years ago, saw one of the most significant increases in atmospheric oxygen, possibly reaching 35% of the atmosphere. This high oxygen environment had a direct effect on the size of certain creatures. Among the first land inhabitants were giant arthropods, ancient millipedes, scorpions, and arachnids. Their unique respiratory systems, which rely on passive oxygen diffusion, were dramatically more efficient in this oxygen-rich air, allowing them to grow to colossal sizes. Some ancient millipedes reached nearly 2 meters in length. One of the most famous examples is Meganeura, a giant dragonfly with a wingspan of about 70 centimeters. While these ancient forests flourished and died, they left behind massive amounts of organic material. Because the fungi and bacteria capable of fully breaking down the tough wood polymers, like lignin, were not yet widespread, this organic matter did not decay fully. Over hundreds of millions of years, these compressed layers, buried under immense pressure and heat, became what we now call coal. Every modern coal deposit is a remnant of these ancient forests that existed 300 million years ago. Meanwhile, large reptiles were emerging, characterized by the development of the amniotic egg, an evolutionary innovation that finally freed vertebrates from returning to water to lay eggs. Among them were the early synapsids and sauropsids. Scutosaurus, heavy, herbivorous creatures resembling massive lizards, were among the dominant plant eaters. And where there were plant eaters, there were formidable predators. The gorgonops, large carnivorous reptiles with long saber-like teeth, were among the most effective hunters of their time, defining the complexity of the terrestrial food webs. The Great Dying, the Permian extinction, the end Permian event. The planet seemed stable, but surface processes were only part of the story. Beneath the crust, immense pressures were building. Around 250 million years ago, in the region of modern Siberia, one of the most powerful and sustained periods of volcanic activity in Earth's history began: the eruption of the Siberian Traps. For hundreds of thousands of years, possibly up to 1 million years, molten rock poured from the depths, forming giant flood basalt provinces across vast areas covering more than 2 million square kilometers. The scale of the eruption was truly staggering, making it one of the largest known volcanic events. As the magma flowed through the crust, it heated up and ignited ancient deposits of coal and evaporated layers of salt, releasing unprecedented volumes of toxic gases and aerosols. The sheer volume of sulfur dioxide, chlorine, fluorine, and carbon dioxide gases released altered the atmosphere globally. Initial sulfur aerosols caused a brief cooling, followed by catastrophic warming from the rising CO2. Acid rain, far more potent than any modern pollution, damaged vegetation, dissolved shell material in the oceans, destroyed soils, and the rising CO2 caused the global temperature to climb sharply. This heating led to a devastating chain reaction. The oceans warmed, causing faster evaporation and significantly lowering oxygen content in the deeper waters. This phenomenon, called anoxia, meant vast areas of the ocean became lifeless. Deoxygenated zones became common, and toxic bacteria flourished, releasing highly poisonous hydrogen sulfide gas, H2S. In extreme cases, the water color changed, turning deep ocean regions pink due to the mass reproduction of certain sulfide-resistant microbes. The H2S may have even bubbled into the atmosphere, directly poisoning terrestrial life. Most dangerously, The warming began to destabilize massive reserves of frozen methane, CH4, a powerful greenhouse gas stored as hydrates beneath the seabed. This sudden release of methane accelerated the warming even further. The planet was trapped in a self-reinforcing climate spiral that drove the globe toward a hyperthermal state. Temperatures rose several degrees above previous norms. Ecosystems collapsed. Roughly 95% of all marine species and a significant portion of terrestrial fauna vanished. This was the Permian extinction, often called the Great Dying, the most extensive mass extinction in Earth's history. The planet resembled a world undergoing a severe reset. The surviving creatures were small, fast reproducing, and highly adaptable, often burrowing or hiding to escape the extreme surface conditions. The Triassic recovery and the rise of the dinosaurs, Mesozoic eon. It took tens of millions of years for ecosystems to begin rebuilding. The immediate aftermath of the Permian extinction was marked by a fungal spike in the fossil record and vast coal gaps, indicating the death of plant life and slow soil recovery. The surviving creatures were small, fast reproducing, and highly adaptable. The subsequent Triassic period recovery was slow and uneven, spanning tens of millions of years. This period saw the rise of the archosaurs, the ancestors of crocodilians, pterosaurs, and dinosaurs, who were better adapted to the hot, arid, and unstable climate of Pangaea. Their efficient respiration and upright stance gave them a decisive evolutionary advantage over the lumbering Permian synapsids. It was in this crucible of recovery that the true dinosaurs began their ascent, eventually becoming the dominant terrestrial life form. Their initial diversity was modest, but they slowly took over the ecological niches left empty by the Great Dying, preparing the ground for their 160 million year rule. By this time, Earth was again dominated by a single supercontinent, Pangaea, stretching from pole to pole. Around 200 million years ago, the climate across Pangaea was continental, hot and arid in the interior, allowing for the evolution of specialized drought-resistant vegetation. In this setting, the first true dinosaurs appeared, a group of reptiles destined to dominate for over 150 million years. Among the early species were the massive plant eaters, often referred to as amphisaurs in early texts, which included the first sauropods, moving in herds across the plains, consuming the lush vegetation that grew near water sources. They were slow, relying on their immense size for defense. Alongside them were fast predators like Dilophosaurus, bipedal hunters that often hunted in packs, using speed and sharp claws to take down prey. These efficient predators quickly established themselves in the new complex food chains. However, Pangaea was not eternal. Around 190 million years ago, the vast landmass began to fracture and split into large fragments due to immense heat flow beneath the continent. This process, spanning millions of years, started with the formation of rift valleys as the crust stretched. Pangaea initially split into two major parts: Laurasia, North America, Europe, Asia, and Gondwana, South America, Africa, India, Australia, Antarctica. A wide depression formed between these masses, slowly filling with water, the Tethys Ocean. This shallow, warm ocean basin was a critical site for future geological events. The currents of this new ocean created nutrient-rich zones, supporting enormous blooms of plankton and small marine organisms. When they died and settled on the seabed, they formed thick layers of organic material. Over millions of years, these layers were buried under immense pressure and heat, transforming the organic remains into oil. Many of the world's major oil reserves in the Middle East and North Africa originate from these ancient Tethys Ocean deposits. While the continents drifted, the oceans became home to the era's largest marine predators. Ichthyosaurs, sleek, dolphin-like hunters, evolved from land reptiles to rule the seas with highly specialized hydrodynamic bodies. They were torpedo-shaped and could reach 6 meters in length and burst speeds of up to 40 kilometers per hour. Alongside them were the plesiosaurs, massive predators with long necks and powerful flippers. Their jaws possess crushing power, often several times greater than that of modern great white sharks, making them the apex hunters of the Mesozoic seas. The continents drift, and mammals hide. As the tectonic plates continued to shift, the Atlantic Ocean began to open. The North American plate separated from the European and African plates. Magma rose to fill the void, creating new oceanic crust along the mid-oceanic ridge, a structure that runs from the Arctic to the Southern Ocean. This slow, continuous seafloor spreading dictated the future movement of the continents, widening the Atlantic by a few centimeters each year. In the shadows of the dinosaur giants, a smaller, less conspicuous revolution was taking place. The first true mammals appeared around 200 million years ago. They were tiny, mostly nocturnal creatures, surviving by their sharp senses of hearing and smell. They possessed fur and nursed their young with milk, traits that allowed them to regulate body temperature more effectively than reptiles. For over 100 million years, they remained small, occupying hidden ecological niches, mostly scavenging for food or hunting insects under the cover of darkness. This small size, warm-bloodedness, and ability to survive on minimal resources would prove to be their greatest advantage when disaster struck. Dinosaurs continue to evolve, filling every terrestrial niche. The massive long-necked sauropods, the armored stegosaurs and ankylosaurs, the fearsome Tyrannosaurus lineage, and the feathered coelurosaurs. Their reign of 160 million years was a testament to their successful adaptation and diversification. The KP impact, an end and a beginning, Cenozoic eon. But even the dinosaurs' dominance could not prevent the event that would reshape life on Earth forever. Around 65 million years ago, a massive cosmic object, an asteroid approximately 10 kilometers in diameter, truly larger than Mount Everest, hurtled toward Earth at over 70,000 kilometers per hour. It impacted the Yucatan Peninsula in Mexico. The sheer kinetic energy was so immense that the asteroid instantly vaporized, excavating a crater over 180 kilometers wide. The energy released was equivalent to millions of atomic bombs, instantly melting surrounding rock into glassy spherules that rained down across the globe. The impact pulverized a gigantic section of the Earth's crust. Massive rock fragments and molten material were ejected globally, followed immediately by a colossal shock wave, earthquakes, and mega tsunamis that ravaged coastlines across the globe. Within minutes, the Earth's surface began to superheat as ballistic fragments returning from the upper atmosphere created a global firestorm. Vast territories were engulfed in self-igniting fires, incinerating plant life and small animals. In the following months, dense clouds of dust and soot blocked the sun, plunging the planet into a long period of darkness and cooling, an impact winter. Sulfur aerosols released from the vaporized rock caused intense acid rain, devastating surface waters and plant life. Photosynthesis ceased, the base of the food chain collapsed, and temperatures plummeted. The lack of food and the harsh environment led to the mass death of the vast majority of species. Roughly 75% of all species, including nearly all large non-avian dinosaurs, perished. The only surviving dinosaur lineage were the birds, close relatives of the ancient theropods. The asteroid impact was a global catastrophe, but it was also the start of a new era. With the large terrestrial animals gone, the mammals finally had their chance. The survivors, those that were small, could burrow or were generalists, suddenly had space to flourish. Over millions of years, mammals rapidly diversified, occupying all available ecological niches, evolving into the large, diverse forms we see today. Their increased brain size and complex social structures marked a new trajectory for evolution. The rise of Homo and the Himalayas. Over millions of years, the mammalian lineage that led to humans began to emerge. Around 47 million years ago, small primates existed in dense forests. One famous fossil example is Ida, an ancient primate discovered in Mesopit in Germany. Ida was an agile creature with large eyes and a relatively developed brain, showing a transition towards the modern primate form. Her exceptional preservation offers a crucial glimpse into the early stages of primate evolution. The unique conditions of the Mesopit, a prehistoric volcanic lake, meant toxic gases killed and perfectly preserved countless animals, including this fragile creature. Meanwhile, the continents were still shifting, leading to the formation of the planet's tallest mountains. The Himalayas are the result of the Indian plate colliding with the Eurasian plate. This continental collision, which began around 50 million years ago, is one of the most powerful tectonic events in history. The mountains grew slowly but relentlessly, their peaks reaching heights comparable to commercial flight altitudes, towering over 8,000 meters. This massive uplift created a permanent barrier for moisture-laden winds, fundamentally altering the climate of Asia. Air, saturated with moisture, rises along the slopes, cools, and loses its water, causing abundant rainfall on one side and creating arid, dry regions on the other. The melting snows on these colossal peaks gave rise to great rivers like the Ganges, Indus, and Yangtze, which would sustain future civilizations. The formation of the Himalayas also sequestered vast amounts of atmospheric carbon dioxide through increased chemical weathering of the silicate rock, contributing to a global cooling trend that paved the way for the later ice ages. This mountain range is not just a geological feature, but a global climate engine. Approximately 2 million years ago in Africa, the species Homo erectus, upright man, emerged. They possessed a brain significantly larger than their predecessors, used sophisticated stone tools, and crucially, controlled fire. Homo erectus was the first hominin species to migrate extensively out of Africa, spreading into Asia and Europe, proving the adaptability of the genus Homo to new climates and landscapes. They followed migratory animal herds and adapted their diets to new environments. Their success demonstrated a major shift from pure biological adaptation to reliance on technology and social complexity for survival. Ice, migration, and the last 6,000 years. The last few million years of Earth's history have been dominated by repeated cycles of ice ages, the Pleistocene epoch. These cycles were driven by subtle, predictable variations in Earth's orbit and axial tilt, known as Milankovitch cycles, which govern the amount of solar radiation reaching the northern hemisphere. Around 70,000 years ago, Earth entered another major glacial period. Massive ice sheets locked up enormous quantities of water, causing global sea levels to drop by over 120 meters. Glaciers move slowly but with colossal power, up to 30 centimeters a day, their thickness reaching up to 2 kilometers in places, carving out valleys, fjords, and canyons across the northern continents. The weight of this ice depressed the land masses, a process known as isostatic adjustment. By this time, a new species, Homo sapiens, wise man, had evolved in Africa approximately 200,000 to 300,000 years ago. This species possessed complex thought, language, art, and the ability to manipulate the environment far beyond any prior species. The lowered sea levels around 70,000 years ago created a narrow, accessible land bridge between Africa and Arabia across the narrowed Red Sea. This event facilitated the single most important migration in human history. A small group of Homo sapiens left Africa and headed into Asia, eventually becoming the ancestors of all modern non-African populations. The migrations continued for millennia. The massive ice sheet expansion in the north created Beringia, a wide, ice-free land bridge between Siberia and Alaska, approximately 20,000 years ago. The journey across Beringia was not a single trek, but a prolonged period of existence for ancient human populations, who may have been stalled in the unglaciated region for thousands of years, developing unique cultural adaptations. The land bridge, which connected Siberia and Alaska, was a cold, arid tundra steppe supporting hardy plant life and abundant megafauna like mammoths and ancient bison. This environment honed the hunting skills of Homo sapiens and forged the founding populations of the Americas. This bridge allowed humans to enter North America, completing the settlement of the final major continent. The ability to sew tailored, insulated clothing and construct robust temporary shelters was paramount to surviving the brutal conditions of the last Ice Age maximum. Around 14,000 years ago, the glaciers began their great retreat. The melting ice formed massive proglacial lakes, which eventually became the Great Lakes of North America. The subsequent collapse of the ice sheets around 14,000 years ago not only led to rising sea levels that submerged Beringia, but also opened up ice-free corridors, allowing humans to rapidly stream south and populate the rest of the American continents, marking the final stage of global human colonization. The planet shed its icy mantle, and the climate gradually stabilized into the interglacial period we enjoy today, known as the Holocene. The last 6,000 years, a mere whisper in Earth's 4.5 billion year biography, have been a period of remarkable climatic stability. The continents took on their familiar shapes, and sea levels rose to modern values, filling the valleys left by the melting ice sheets. In this brief stable window, human civilization emerged. We built the first settlements, learned to cultivate the land, created cities, and explored the sky. But to the Earth, this is just a fleeting chapter, a thin line on a monumental timeline. Today, Earth continues its slow, geological life. Plates shift beneath its crust. The hot mantle material circulates in its depths. Rivers are born and die on its surface. It remains an active yet remarkably resilient world. Everything you see around you, the forests, the oceans, the mountains, is the product of countless processes that began billions of years ago. When we look at Earth today, we see not just a planet, but the culmination of a long ancient biography, a story where every era, every glaciation, every eruption, and every silent millimeter of lithospheric movement created the very conditions for us to be here. If you feel your eyelids growing heavy, allow the grand story of life on Earth to wrap around you gently and guide you into calm. Don't forget to subscribe to listen to more of our bedtime stories. Close your eyes, take a deep breath, and slowly drift into sleep, into silence, into the boundless, timeless current where all life intertwines. Wishing you a quiet, comforting night.